This is lesson 9 of AP Precalculus. Today we're going to be discussing section 1.4 parts A and B. Before we do that, let's go ahead and review what we have covered in section 1.3. We looked at 12 different types of basic graphs, basic functions that we will be studying throughout the course of this year. The first one was the identity function, where it looks like a straight line. We looked at the cubic function, where it goes from negative infinity all the way to positive infinity ROI. The square root function, you had an example of that in last night's homework. The natural log, which you also did in last night's homework. Then we have the different sine, cosine, and tangent functions. Here we're looking at the sine and the cosine. They're very similar ones, just shifted from the other. Then we had the integer type functions, or a step function, which we worked in one of our homework problems last night, as well as the square function, which was also one of the very first problems that you had in homework last night. The reciprocal function looks very similar to a square root or a natural log, but it's rotated a little bit, and there are two of them. We had the exponential function, which is kind of the inverse of a natural log, not exactly, but it has that kind of shape. The absolute value, which gives us more of a v, and then a logistic function where we do have asymptotes, so we have a maximum and a minimum point. Those values get closer and closer to those particular values, but never actually touch. And we're going to be looking at several examples of that as we go through the year. So we're going to start out today by looking at combining functions algebraically. What are the four basic operations in mathematics? It would be addition, subtraction, multiplication, and division. In elementary, you likely learn them in that order: how to add, then how to subtract, how to multiply, and then how to divide. We can do similar operations with functions. They just look a little bit different as we notate them. So to start off, let's look at the addition type. Here we have f plus g of x. That is the same as saying f of x plus g of x. So we take each function and we add them together. If we did subtraction, it would be f minus g of x. So that's the same as taking f of x and subtracting g of x. If we were to multiply fg of x, that would give us f of x times g of x. And of course, division, we would have f over g of x, which is f of x divided by g of x. Now, in this particular one, this division one, we do need to be careful because we cannot divide by 0. So there are going to be extra restrictions on our domain that are possible because we cannot have the value of g of x being equal to that of 0. In all of these cases, we are going to be limited to our original domains. There may be an additional restriction on that division one, as I just explained. So let's work out an example. Let's just say that we have f of x being equal to x squared and g of x being equal to the square root of x plus 1. Here we want to find f times g of x. So if I take my f function, that of x squared, and I multiply by my g function, the square root of x plus 1, I get x squared times the square root of x plus 1. Now the question now becomes, what is our domain? We want to make sure we include our domain because not all numbers may be possible. Well, if we look at our original function of f, that is x squared. What is the domain of x squared? It would be all real numbers. I can plug in any value and get a value for my function. If I look at g of x, I have the square root of x plus 1. Well, what is my domain on that? My domain on that particular function only goes from -1 to infinity. I cannot place a -2 or any other negative value that's less than -1 in that function. If I were to do that, I'd get an imaginary number, which would not work. So I'm limited to values of -1 and above. Well, the same is going to be true when I multiply my two functions together, and I get something like this. My domain is still starting at and including -1, going all the way out to positive infinity. What would happen if we were to subtract these two functions? Same two functions, but now we're going to subtract g from the f. Well, I would take my original function of f, which is x squared, and I'm going to subtract my function of g, which is the square root of x plus 1. Looking at the domains, once again, my x squared function, all real numbers. My g of x, I have to start at -1 and go out to positive infinity. So my domain of my new function is going to be the same, from -1 and including that all the way to positive infinity. So let's try the addition one. Here I'm taking f and I'm adding my function of g, so that would give me x squared plus the square root of x plus 1. My domain, once again, starts at -1 and goes all the way out to positive infinity. And the final one, the division. Let's take f and divide by my function of g. When I do that, I'm going to have x squared divided by the square root of x plus 1. So what is my domain here? Well, my domain would, based on my original functions, have to start at -1 and go all the way to positive infinity. However, since we are dividing by one of my functions, I do want to take a little bit of extra caution and make sure that that denominator is not equal to 0. Well, when is the square root of x plus 1 equal to 0? That is going to occur at -1 when my x value is equal to -1. So I cannot include the -1 value in my domain, which means my domain goes from, but not including -1, all the way to positive infinity. So as you will know on the board is that on these, all of our previous ones, the -1 was included, whereas on my final answer here with the division, my -1 is not included. Let's try a little bit different. We're going to take the same g function, but instead we're going to find g times g of x, or g squared. So if I square the square root, I end up getting simply x plus 1. Now the question becomes, what is my domain for this particular function? Well, since my original domain had to be from -1 all the way to positive infinity, even though when I square it, that would go away, my domain still has to remain from -1 to the positive infinity. So don't go by just the final answer, because in this particular function right here, we could have all real numbers from -infinity all the way to positive infinity. But because it came from a limited or restricted domain, I need to use that restricted domain in my final answer. And now for part B of section 1.4, the composition of functions. When you write a composition in English class, that means you are taking pieces of information and you're compiling them into something that has a sequence, has a pattern to it, has some sort of logical process in your thought process. Composition of functions are going to be something that is very similar. We are taking different functions and we are combining them in a certain order. The easiest thing to do is just to show an example in order to teach this, but I do want to look at the way that it is written first and foremost. So here we have f composed of g of x. So what this means is that I'm going to take my g of x function. If I find the value for that, I'm going to substitute in that g of x value as my x value in my f function. Let me show you an example. Let's just say that f of x was 2x and g of x was x plus 7. I want to find out what f composed of g of x is. I'm going to take my g of x value here, the x plus 7, and I'm going to substitute it in for the x value in my f function. So that's going to give me 2 times, instead of x, I now have my g of x value, x plus 7. I can then simplify that by distributing the 2, giving me 2x plus 14. Now, what about the domain of my composed function? We do want to double check, because when we compose, we are going to be limited to the domains of our original two functions. However, there may be extra restrictions, so we always want to double check. In this particular case, if I just looked at this function right here, x could be anything. X could be a positive, it could be a negative, it could be 0. There really are no restrictions on that particular domain. If I look at 2x, again, no restrictions on that particular domain. When I look at x plus 7, no restrictions on that particular domain. So my domain for my composite function is going to be from negative infinity to positive infinity. There are no restrictions on my domain. I do want to point out that in most cases, not in every case, but in the vast majority of cases, if I compose f from g, I'm going to get a different equation than if I compose g of f. So very seldom are these two functions going to be equivalent. So it's not like multiplication where I can take 5 times 8 or 8 times 5 and come up with the same value. Here I am composing, so it is going to be different functions as my final answers. Let's try a few other examples. Let's say that f of x is equal to e to the x and g of x is equal to the square root of x. I want to find f composed of g of x. So that means I need to take my g function and substitute in this particular case, the square root of x, for my x value on my f function. So that's going to give me e to the square root of x power. Now, if I take a look at my original domain, in this particular case, my f function, there are no restrictions. I can plug in a positive value, a negative value, a 0. Anything goes for my x value in my f function. If I look at my g function, however, it is a square root of x, which means I cannot have a negative value. It can start at 0 and go all the way out to infinity. So that is going to limit my domain for my new composed function. I'm going to be able to start at 0, go out to positive infinity. But we also need to take a look at my final value here. Can I use a 0 for x in my composed function? The answer there is yes. Can I use any positive value for x? And the answer there is also yes. So my domain ends up being from 0, including 0, all the way out to positive infinity. What if we were to reverse these two? If I were to compose g from f, well, now I need to take my f function, which is e to the x, and I'm going to substitute it in for my x value in my g function. So now I have my composed function being the square root of e to the x. So what is my domain here? In this particular case, I can plug in any value for x, and my composed function will indeed work. So when we compose functions, we are creating a brand new function that, even though it is based on previous functions, we are acting as though it is a completely new function by itself. If I were to graph both of these functions, and I color-coded them in the blue and the red, my function here, the f composed of g of x, It starts at 0. It has a domain going from 0 to infinity. So that's this blue line right here, what appears to be a line. It's not actually a line. The red function here, g composed of f, I have a domain that goes from negative infinity to positive infinity. So I can plug in any value for x and it will work out in my composed function. Let's try another one. Let's just say I had f of x being x squared minus 1 and g of x being the square root of x. I want to find out what is f composed of g. So I'm going to take my g function, which is the square root of x, and I'm going to substitute in for my x value in my f function. So I now have the square root of x squared minus 1. Well, the square root of x squared is simply x, so I have x minus 1. So what is the domain for x minus 1? So since my domain of my original x function could not include anything that was negative, I have a domain that starts at 0 and goes all the way out to positive infinity. If I were to graph my composed function, you will see that it starts at 0 and goes out toward that positive infinity. What about g composed of f? And so now I'm going to take my f function, which is the x squared minus 1, and substitute it in for my x value in the square root. So that gives me the square root of x squared minus 1. What is the domain of this function? Well, I have to have x squared being greater than or equal to 1 because I cannot subtract 1 from it and get a negative number. Otherwise, I'm taking the square root of a negative. So if I solve separately, I will get either a negative 1 or less, or a positive 1 or more for my x value. So my domain is a union of sets. It goes from negative infinity to negative 1. And then picks up again at 1 and goes all the way to positive infinity. The negative 1 and the 1 are included as part of my domain. If I were to graph this particular function, you will see that it does indeed have two different offshoots of the graph. So it is disjointed. So that brings us to reversing the composition. So decomposition of functions. It can be a little bit more tricky, a little bit more of a challenge. One of the other pieces that makes these a little bit more of a challenge is the fact that there could be multiple answers to the same question. So we could decompose it in different ways and it still be legitimate. As an example, if h of x is equal to x plus 1 quantity squared minus 3x plus 1 plus 4, what would f and g of x be if we had h of x composed of f and g? There may be several forms that we can use. The first thing, and I'm going to look at, is I look at these parentheses. I have an x plus 1 and an x plus 1. Those sets of parentheses are exactly the same. So what if I were to say, well, what's in parentheses here is my g of x function. Then my f of x function would be my x squared minus 3x plus 4. That would be one way of working this one out. So you look for similarities between. In this case, the similarity is the x plus 1. So if I set that as my g, then my f would then be x squared minus 3x plus 4. And we have decomposed it into two functions. Now that is not the only way of decomposing this particular function. There may be several others. If we were to distribute combine like terms, we might find other ways of decomposing it. But I would encourage you to look for one of the more simplistic methods as opposed to jumping through a bunch of hoops. Let's try this one. If h of x is equal to the square root of x cubed plus 1, what would f of x and g of x be if h of x were a composition of f and g? So here I see that I've got a square root and then I've got cubed roots inside. I might go with a simple way of saying, well, I'm going to take f of x being equal to the square root of x, and I'll have g of x be equal to x cubed plus 1. I could break that down, and I do come up with a correct way of decomposing it down. But that is not the only way. Another alternative would be to say that f of x is the square root of x plus 1, and g of x is simply x cubed. If I were to substitute in this x cubed into my f function, I would get exactly what we have up here at the top, where I had my composition already written out for me. The volume of an angioplasty balloon inflated at a constant rate is V equals 8/3 pi r cubed, where r is the radius of the balloon. If the rate is 44 cubic millimeters per second, what is the volume after t seconds? So we're moving into the application portion of what we've learned. We will start out by simply looking at the equation, read it through one time, get a basic idea, and then you might want to read it through another time to get a deeper understanding. So as we solve these types of word problems, I'd encourage you, read it through just the first time just to get a basic understanding. Don't try to encompass everything all at once. Break it down into smaller, usable, biteable chunks. So the first thing I'm going to start with is I need to know what my volume is. My volume is 44 cubic millimeters per second. That's the change in my volume. And so if I write that down as V is equal to 44 cubic millimeters per second. And since I'm using T as the number of seconds, I could write that as my volume at any one particular moment in time is going to be 44 cubic millimeters times the number of seconds that I'm allowing that angioplastic balloon to enlarge. And so that it would be my final answer. Let's do another problem, also working with this angioplastic balloon. When the volume is V, what is the radius? So now I'm taking my original equation of 8/3 pi r cubed, and I'm solving for r instead of for V. So to do that, you could multiply both sides by 3 to get rid of the fractions first, and then divide both sides by 8 pi. That would give me 3/8 V is equal to pi r cubed. If I divide both sides by pi, and then take the cubed root of both sides, I can solve for r. So r is equal to the cubed root of 3v over 8 pi. Now we could rationalize that and do some other things, but generally speaking, when we have something that's a little bit more complicated, such as this answer, we're just going to leave it in that form. Write an equation that gives the radius as a function of time. We're going to use our v equals 44t, and we already solved that r is equal to the cubed root of that. So now we're going to take those two pieces, put them together, and try to solve. So if we substitute in the 44t for my volume here, I can go ahead and multiply. I then reduced down as much as I could, and that gives me the cubed root of 33t all over 2 pi. Again, we could rationalize that out. We could also come up with decimal equivalents, but if they wanted the exact answer, which they do here because they want us to write the equation, we're going to leave it in that particular form. What is the radius at 5 seconds? So now that I've solved, I need to find my radius and t being equal to 5. So I'm going to use my new function here, substitute in a 5 for my t value. So 33 times 5 is 165. Divide that by 2 pi, take the cubed root of it, and you get approximately 2.972 millimeters would be the radius of that particular angioplastic balloon. So that is the lesson for today. Today we learned about composition of functions as well as the basic operation of functions where we're adding, subtracting, multiplying, or dividing. Let me remind you that when we do addition, subtraction, multiplication, and division, our domains are going to be whatever the original domains are, with the possible exception of the division one. There might be extra restrictions on your domain. So you want to make sure that you do figure out those extra restrictions on the domain and place it in your final answers.